What's up, guys? Back at it again with a new lab, Lab 5, Falling Magnet Faraday's Law. And it's your boy, Andrew Leonard. So what we needed for this lab was just a magnet, some tinfoil, and we used some software from GlowScript. And the goal of this lab was to find out how dropping a magnet through a tinfoil tube and seeing how long it takes to fall out. And we simulated this all through GlowScript and see how it compares to the actual data. And then you can see here's the magnet that we used. Now the experiment. So we set it up with one tinfoil tube that acts as a conductor, and we drop a dipole magnet to see how long it takes to fall out. Now, the results of this lab is said it took 0.345 seconds to drop. That is absolutely insane. Now here you can see the video we recorded, and as you can see, you can drop it, and it came out in that short amount of time. Okay, there we go. Now the code introduction. So we used some sick code here, but in order to do that, we needed some physics concepts before that. So first we wanted to use Faraday's law, and we wanted to see the change in flux to see what current it induces on the tube. Why do we want to do that? Well, we also wanted to use the PHYS law to find the magnetic field from the magnet that exerts on the tinfoil. We wanted to calculate the force on the tinfoil, and using Newton's second law, Newton's second law, you heard that right, it used the action-reaction forces, and we want to know the force of the tinfoil on the magnet. Now we combine all those, and we use the force formula, which is IL cross B. Yes, that's what it is. And we use the Faraday's law from the I from the Faraday's law, and we use the B from the Biot-Savart law, and we get the force on the magnet. Now, how is that put into the code, you may ask? So easy. We use the magnetic field from the dipole. Sorry. So we use the magnetic field from the dipole, and we use it on the top image as you can see here. Then we calculate the magnetic flux from the dipole as well in the second image. We use these formulas which were given through us from the labs, from previous lectures. And lastly, we wanted to find a force on the magnet by the tinfoil. But how do we do that? Well, first we want to find the current induced on the tinfoil using Ohm's law. We know the EMF from Faraday's law. We divide that by resistance of the metal, and we find the current. Now we also wanted to calculate total magnetic field on the tinfoil. So we use the Biot-Savart law using the first definition we found up top, and we found the magnetic field on the tinfoil from the magnet. Now all we have to do is plug it into I delta L cross B, and we found the force on the tinfoil. And knowing Newton's second law, that is an action-reaction force, so that is equal to the force on the magnet. Now we just have to simulate the movement of the magnet using Newton's first, second, and third laws. Now the results, the moment you've all been waiting for. We found that it took 0.333 seconds for the magnet to go down the tube. This is compared to 0.345 seconds from the experiment. Both are extremely close to one another. Notice that while it's falling through the tube, the magnet has no acceleration, which you know what that means? It has no net force, which means that the gravity is equal to the force of the tinfoil on the magnet. Now conclusions. What if the resistivity of the conductor was reduced closer to zero? This means that the current induced on the metal would have to be higher. If we substitute this larger value into the equation for the force of the magnetic field, we'd get a larger force. And this means the magnet would take longer to fall. What if there were holes or slots were cut into the tinfoil? The induced current would be smaller due to the fact that there are less rings of material to slow down the magnet. In the force equation, if we wanted to look at it mathematically, we see that means the L component would be less. Therefore, the force would be less and it would take less to fall down. Thank you guys. Make sure to hit the like button and subscribe. Hit me up on Instagram and at Andrew Leonard and on TikTok as well. Thank you so much, guys. See you next time and peace.